Looking at the x of t and y of t graphs, I'm sure many Algebra 2 or Pre-Calc students would think, hey, those look like piecewise functions. And you should think that. In typical circumstances, that is absolutely what we would use to model these graphs. By the way, if you don't remember what piecewise functions look like algebraically, here's a piecewise definition for x of t. Piecewise functions are the most efficient way to define such curves, and I'd be dismayed if my students didn't even think of them when looking at these graphs. However, maximum efficiency is not our primary motivation in this pursuit. We set out to determine a single pair of parametric equations to define a complicated curve, and doesn't a piecewise definition seem antithetical to the spirit of that pursuit? In the same way that I argued that the 2011 Batman equation felt more like 6 equations sandwiched together rather than one equation, to me this feels like 7 separate equations duct-taped together. In your mind, if this doesn't violate the one equation aesthetic, then your job is almost done. You'd just write another similar definition for y of t, figure out how to format a piecewise parametric pair for your particular graphing software, and then call it a day. I cannot settle for that in good conscience though, so in the next steps I'll show how we can merge these various pieces of the piecewise function into one non-piecewise function. For the time being, let's focus our attention on merging the first 3 linear pieces of x of t. There we are, zoomed in. Let's call these pieces x1 of t, x2 of t, and x3 of t. And say that big X of t is the sum of those 3 pieces. Now, if we're thinking of these as functions, there's a bit of a conceptual problem here. It's very similar to one of the problems with the original Batman equation. Notice the domain of x1 is the set of t values between 0 and 1. The domain of x2 is the set of t values between 1 and 3. The domain of x3 is the set of t values between 3 and 5. There are no t values that are common to the domains of all 3 functions, and therefore the domain of big X of t is the empty set. So if you type such a big X of t equation into a grapher, you'd end up with an empty coordinate plane. The restricted domains of the pieces are the source of the problem, so we need to unrestrict them so that each of these graphs individually will have all real numbers in their domains. Let's extend x1, giving it a constant output as we extend it to the left, and this constant output as we extend it to the right. We'll do the same for x2 and x3, extending them to the left and to the right. There. Now, all 3 of these individual functions, as well as their sum, big X of t, contain all real numbers in their domains. This is another moment where I'm hoping that you have enough previous experience, this time with function addition, to buy what I'm selling. We'll find later that when you add these 3 simpler functions, x1, x2, and x3, what you actually get is a vertical translation of the function that we really want. So later we'll determine a constant c that we can add to correct for that.